Hi everyone, welcome to Mathemly. Hi everyone and welcome to our series on neural networks. In the last video, we explored the limits of simple linear models and saw why straight line boundaries can't handle complex data. In this video, we will see the magical ingredient that allows neural networks to bend, twist and adapt to data, non-linearity. We will also see how adding layers of these non-linear transformations give networks their real power. Let's start with a reminder. A single weighted sum of inputs like z equals x to the power t times w plus b can only create straight lines as decision boundaries. That is fine when your data is linearly separable. But real-world data often curves, clusters, or forms patterns that a straight line can't capture. This is why we apply an activation function written as shown in the screen. It transforms the output into a non-linear shape. Think of it like taking a rigid ruler and bending it. Suddenly, you can trace complex boundaries instead of being stuck with straight cuts. Now, let's see a bit more about the activation functions. Each of them has a unique way of bending data and shaping how a neuron responds. Step or sign function. This is the simplest. It outputs one class if the input is above a threshold and another if it is below. It is easy to understand but not smooth, which makes it hard for the networks to learn. Sigmoid function. A smooth S-shaped curve that squashes values between 0 and 1. This is perfect for probabilities and it is often used in the final layer of binary classification tasks. Tan-H function. Similar to sigmoid but outputs between -1 and 1. Because it is centered at 0, it helps the learning progress more smoothly. ReLU or rectified linear unit. The most popular choice in modern deep learning. It outputs 0 for negative values and grows linearly for positive ones. Simple, efficient and powerful. Gaussian function. This is bell-shaped and great for detecting localized patterns. It is less common in standard networks but very useful in specialized models like radial basis. Adding a single activation function allows a neuron to bend the decision boundary once, but the real power of neural networks comes from stacking multiple layers of these transformations. Each layer follows the same recipe. It takes the inputs, computes a weighted sum, applies an activation function to introduce non-linearity, and then passes that result forward. When we stack several of these layers, each layer builds on the transformations of the previous one. You can think of it like stacking sheets of flexible glass. One sheet might bend the data slightly, the next bends it further, and with several layers combined, the network can twist and shape the data space into something highly adaptable. This process allows the model to capture very complex relationships, like wrapping around a circular pattern of data or separating interwoven shapes that no single line or even a single bend could handle. In other words, layers give neural networks their depth, and it's this depth that allows them to learn patterns far beyond the reach of simple models. Activation functions aren't just abstract math, they power real applications. Sigmoid is used when we need probability outputs like predicting whether an email is spam or not. ReLU dominates in computer vision, making it possible for systems like self-driving cars and facial recognition to learn quickly from huge image datasets. Tan-H has been used in sequence models where zero-centered outputs are useful. And specialized activations like Gaussian appear in anomaly detection or pattern matching problems. To sum up, nonlinearity is what gives neural networks their flexibility. Activation functions like sigmoid, Tan-H, ReLU, and Gaussian each shape how data flows through a network, and stacking them in layers allows networks to model even the most complex patterns. In the next video, we will zoom in on the fundamental building blocks of every neural network, the neuron itself. We will explore how inputs, weights, and biases come together to form a neuron's decision, and how that simple process becomes the foundation of powerful learning systems. If you found this video helpful, don't forget to like, share and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.